All righty, let's get started. So today we are moving on to our final major topic for the semester. So this is going to carry us to the end of the semester. And that is light. Basically, we're talking about light and in fact, light and optics. So this is a very large topic. It's one I find quite interesting. And in fact, a lot of it is more interesting, more fun. The calculations are okay. Not too many big time equations to worry about, but a lot of conceptual stuff and a lot of thinking about light in ways you don't necessarily do in your normal life. I mean, obviously we just take it for granted, but it's very rare that we ever think about what light actually is, how it works, and all this kind of stuff, even though a great majority of our lives is dependent on other people having figured out a lot of stuff about light, and thus making our lives better or easier because they know how to manipulate it. So to get into it, the first thing we have to do is figure out, what do we mean by light? What is light? Of course, we have a very simplistic view of light. Everybody does. We know when it's light outside or when it's dark. But there are a bunch of things which are light, which we don't consider to be light. For instance, radio. Every time I've talked to somebody that doesn't already know, and I say radio is light, they say, no, radio is sound. Obviously, we listen to the radio. We don't see the radio. But that's not true. Actually, radio waves, the things which your actual radio device takes in, that has the information built into it that then is played through the speakers, is light. It's just light that we cannot see visually. And that's because our eyeballs, the cameras of our body, the things we use to detect light are not perfect. Just as is true of any camera that's ever been created, there's only a certain range of light which can be seen. Now, for our eyeballs, we call that visible spectrum, the visible light. And for a radio, it's radio waves. And if we have fancy cameras that can see infrared, like the heat signatures and things like that, then it could see a different range of light than just what's called visible light. There's a huge wide range of light. Each we break it up into certain ranges, which is just arbitrary. There's nothing different between a microwave light or radio light or X-ray light and visible light or gamma rays or ultraviolet. They're all the same thing. They're made of the same substance. There's just a particular characteristic about it, which can either be seen by our eyes or seen by a camera sensor or felt, or all sorts of stuff, the way it's detected. And so in order to get a better grasp of what light is, we have to introduce, of course, what it's made of. And it turns out that light is a combination of two things, and that is called the electric field and a magnetic field. So, of course, to talk about this, just to introduce it a little bit, an electric field is kind of this abstract thing we try to visualize that tells us how a charged particle, so let's say we have a proton or an electron, that's a particle with a charge on it, an electric charge. And because it's charged, it can manipulate other charged particles around it. For instance, if you have two protons close to each other, they want to repel each other. because like charges repel, unlike charges attract. You have two electrons close to each other, they want to push each other away. And so one way for us to visualize the ability for the electrons to push each other away is we say there is an electric field. So here's your electron. There's electric field which comes out of the electron or goes into the electron more specifically, if I'm going to be appropriate about it. And the other electron, same thing. And what happens is the electric field between these charged particles kind of interact with each other. And when they interact, that kind of tells the particle how to move. So if you have two electrons near each other, their electric fields interact with each other and change shape. And the way the electric field is shaped tells the electron how it can move. So it'll follow these lines of electric field. And when the two charged particles interact, because they change how those lines are actually felt. So if these are two electrons, after they interact with each other, the lines all go kind of like this. And so this electron will be moved that way, and this electron will be moved that way because it's following its electric field. Now, can you actually see an electric field? No. What is it the charged particle is actually changing or manipulating? I mean, it's not manipulating the air. It's not making the air move differently or something like that. This is more of an abstract model to help us visualize. But whether it's real, whether there's an actual physical substance called the field, well, no. You can't go grab a piece of the field. It's just the universe, the space in which all these things are placed, kind of contains this interaction, and that's what we call the field. We don't need to get very much into it. If we wanted to, then we'd study electricity and magnetism at a much deeper level. But for now, electric charges produce electric fields, and the electric fields basically tell the charges how they're allowed to move at the end of the day. And the same is true of magnets. If you have a magnet, so let's say we have a bar magnet, one side's the north side, let's say, and the other side is the south pole. And the same kind of a thing holds true here. If you have two magnets, if you put the two north poles together or close to each other, they repel each other and the south poles attract each other. And so the same thing. We get magnetic fields, which kind of look like this. And magnetic fields interact with each other the same way. When you have two magnetic objects, you bring them close, their fields interact and kind of move and change how they're placed. And that will show you how the magnet would want to move. So you have electric fields and you have magnetic fields. You have charges and you have magnets. Well, it turns out that more deeply, magnets and electric charges are actually kind of the same thing, even though they don't seem to be. A magnet is a magnet. Magnets attract other magnets or other things which can be magnetic, and electric charges are charged particles. They're different. That's why we call one electric and one magnetic. But when you go to learn about how these things work, what you find is a magnet is only magnetic because it's got electric charges within it. And it's how those electric charges are aligned that will make something magnetic or not. There's nothing special about the material of a magnet. I mean, you could have a piece of wood. A piece of wood has electrons in it. It's made of atoms. Atoms have nuclei and it's got electrons. Metal, it's got nuclei, it's got electrons. It's the same materials. But the reason a piece of wood is not magnetic, whereas a piece of iron is magnetic, is based on how the electrons in that material are aligned. If all the electrons are lined up in a very specific direction, then that object is called magnetic. If the electrons are not lined up, but they're just randomly oriented, which is what's true in a piece of wood, let's say, then it's not magnetic. And so it turns out that deep down, magnets are, or magnetic phenomena, are really kind of a form of electric phenomena. It's not exactly, because it turns out to make something magnetic, you have to have something that's electrically charged and it's moving. Whereas electric is just electric charge. It can just be standing still and it'll be electric charge. A magnet has to have something about the electric charge moving, whether it's spinning or literally moving around in certain directions, whatever the case is, it is the motion of the electric charge which causes magnetic properties. So it turns out electric and magnetic fields are kind of built within each other. And in fact, this is something that's called electromagnetic induction. Very fancy word. And all it means is that if you have, let's say, an electric charge, a particle that's charged, and you move it around, that'll induce, like create or induce a magnetic field. So if I have, let's say, here's an electron, and I take it and I just move it up and down like this, just kind of move it up and down, then what winds up happening is you get this magnetic field, a wave of magnetic field coming out. And so by having an electric charge and moving it, you induce a magnetic field. And the same holds true of a magnetic of a magnet. If you take a magnet and you move it around, you create an electric field. And we know this is true because a lot of our electronics rely on this. People have done experiments where, for instance, you have a wire and you send current running through the wire. If you put a compass underneath this wire, which has current running through, remember a current, or just to let you know, current running through a wire just means there's electrons moving through the wire. Okay, so you have charged particles, electrons, as they move through this wire. That's a moving electric charge that induces a magnetic field, and that magnetic field can mess with a compass needle. And so you can have the compass not point north anymore because you have electric charges moving. And of course, we could do the same thing. There's an experiment you can do where you take a coil of wire. So I'll try to draw this out. Let's say here's a coil of wire. Okay. And we hook this up to a little machine that'll tell us how much electricity runs through the wire. And it's not plugged into power. It's just a wire sitting there, plugged into this little meter. And it tells us, is there power running through the wire or not? And of course, since it's not plugged into the wall, it's not plugged into any power source, there's no power. It doesn't do anything. It's just a piece of wire sitting there. But then if you get a magnet, so here's your North Pole, here's your South Pole. If you put a magnet into this coil and you move the magnet around, all of a sudden you get current running through the wire. Power starts to go through. And so if this is a little meter, you'll get the meter to tell you, hey, all of a sudden we got a current flowing through this wire, which is weird. Just by moving a magnet around, you're able to create electricity. That's another form of electromagnetic induction. So both of these forms are sitting there. By moving charged particles, by changing electric fields, you can induce a magnetic field. And then by moving a magnet, by changing a magnetic field, you can induce an electric field. And that's because deep down, fundamentally, electricity and magnetism are kind of the same thing. It's just we visualize them or see them different, but they're really deep down the same. Now, this electromagnetic induction is very important because if it's true, which of course it is, but if it's true that if you move an electric charge, you create a magnetic field, well, this magnetic field is moving along as a wave, and a wave, of course, is moving up and down. So that means as this magnetic field is moving through space, it's a changing magnetic field, and a changing magnetic field induces its own electric field. And of course, now that you have this electric field being created by a magnetic field, as that thing moves along in space, that's a moving or a changing electric field. So it induces another magnetic field. And so you get this kind of system of you move an electron, it induces a magnetic field that moves, and that moving magnetic field creates an electric field that moves, which creates another magnetic field that moves, and so on. And you create this wave of electric and magnetic fields which move through space. And that is exactly what light is. Light is exactly defined to be electromagnetic radiation. It is nothing more than an electric field and a magnetic field moving together through space. And it's got certain properties. The first main property is that, let's say we have the electric field. Here's the electric field as a wave. As the wave moves to the right, the electric field is going up and down, up and down, up and down, and so forth. Okay, moving along that way. And of course, because this is a moving electric field, a magnetic field is induced. But here's the thing about the magnetic field. It turns out that every time an electric field creates a magnetic field, or vice versa, they're perpendicular to each other. And so if the electric field is waving up and down, then the magnetic field, let's say the way I'm going to draw it, is moving forward and back. So if I were to try this, and I'm not good at this three-dimensional stuff, but it kind of looks like this, where this green is supposed to be the magnetic field. Let's say this is the center. And so that green is kind of coming out at you this way and going back away from you that way. Okay, so if you try to visualize it three-dimensionally, you have the black wave, which is the electric field, moving up and down as it moves to the right. It's waving up and down. And then the green is its own wave, but instead of waving up and down, it's waving forward and back, and it's still moving to the right. And so this combination of these two waves, the electric and the magnetic field, is exactly what light is. That's all it is. Now, what's interesting, or what's kind of strange, what makes light so weird to us, is that this wave is not a wave of a material. You know, if we think of something like a water wave, well, that's, you know, something pushed the molecules of the water in a certain way. And so it's the water molecules moving through the ocean or through the lake or whatever it is. And the way they move, they create waves that move up and down as they move towards the shore. But the thing which is waving is water. It's the actual molecules of the water. Or sound waves. That is, your vocal cords as you speak vibrate, and so they kind of push back and forth the air molecules that's in the air, and as those air molecules vibrate, they move towards other objects, and they can reflect off, or they can be absorbed by the ears or felt by the ears. And so it's the air molecules that are vibrating with sound. With light, it's not air, because we can have light travel through space. There's no air in space. In fact, there's no particles at all in space if we want to think about actual empty space. So what the heck is the thing which is waving? It turns out it's this electric and magnetic field, which is kind of weird because, as I said at the beginning, electric field and magnetic field is kind of our own visualization of what's happening. It's not actually a physical substance that you can touch. Water you can touch, so a water wave makes sense. It's the actual water itself waving. But here we have electric fields and magnetic fields waving. But that's the way it is. And what this allows to happen is it allows light to travel even when there's no material, when there's no particles there. So we get light coming from stars from outer space, because even though there's nothing to wave out in outer space, there's the field, the electric and magnetic fields, which can wave. And that's what we call light. So conceptually, that's what it is. When someone says light, they mean electromagnetic radiation, and that's the basic premise. From here, what we find, there's several characteristics we can talk about, which define the light. What color is it, for instance? How bright is it? Things like this, which we'll discuss. What type, for instance, as I said, radio waves is a form of light. Microwaves are a form of light. X-rays, visible light, the things you see. So what makes all those different quote unquote types of light? Well, they're not different types of light. They're all just light. It's just our own human experience chose to say light, which vibrates like this, we'll call it an X-ray. And light that vibrates like this, we'll call it a radio wave. It's still electromagnetic radiation. There's no difference between radio and visible light, or between X-rays and ultraviolet. They're the exact same thing. It's just how they vibrate, how fast they are, is basically what tells you this. So, some physical characteristics which are important to understand about light, other than the fact that, of course, it's electromagnetic radiation. Well, the first thing to know that makes light the most special thing in the universe, and also the most confusing thing in terms of physics, is the fact that light has a speed. Light moves at a certain velocity. Now, that's not so weird. Sound moves at a certain velocity. There's something called the speed of sound, velocity of sound. And it turns out the velocity of sound in air, let's say, is 343 meters per second. So if you've ever, let's say, maybe you're watching fireworks on New Year's or the 4th of July, and the fireworks are kind of far away, so you're watching someone else set off the fireworks. And you see the firework explode, and then you hear it a second or two later. Well, that's because it took some time for the sound to travel from the exploding firework to your ears. And that's because, of course, light or sound travels at a certain speed. And so if you're 2 or 3 miles away, well, it takes a certain time for the sound to get to you. So it's not so weird that light would have a speed. But it turns out that's what makes light the weirdest thing we've ever seen, and I'll explain it. But for our purposes, the speed of light has its own special variable because it's so important, and that variable is c, little c. So in physics, pretty much in any science, if you see the variable c, for most part, it means the speed of light. Of course, we already saw in thermodynamics, speed of, or the specific heat also had the variable c. But generally speaking, in physics, when you see the variable c, we mean the speed of light. And it is, after rounding a little bit, 3 times 10 to the 8th meters per second. That's a huge, huge number. 3 with 8 zeros after it. Think about how much bigger that is than the speed of sound. And the speed of sound is fast. I mean, it was an impressive feat for people in jets to get up to the speed of sound. And that's only 300 meters per second. Light is 3 times 10 to the 8th. So that's like 3 billion, nearly. So it's a huge, huge number. That means light travels very, very, very quickly. In fact, it travels so fast that for pretty much all of our everyday experiences, we don't even see the effects of the speed of light. We turn on the light switch, the light is on instantly. It's not like the light bulb turns on and a second later we see it because the light had to travel from the bulb to our eyes. It moves so fast that we see it instantly. You'd have to be extremely far away to start to see the effects of the speed of light. And even then, you can't directly see it because there's no way to know when the light, for instance, let's say someone's on the moon and they shine a laser pointer towards you and you see it. Well, when you see it, you think that's when the laser pointer was turned on. There's no way for you to know when it was actually turned on versus when you saw it, because there's nothing that it can actually travel faster. Someone can't tell you, hey, I just turned on this light. Do you see it yet? And then you see it later. Because by the time the information gets to you to tell you they turned on the light, well, the light was already there because it moves faster. But nonetheless, this is a finite speed. It's not infinite. And that means that it will take some time for light to travel. For instance, here's a question. We're the Earth. Here's the sun. There's the sun. And we're the Earth way over here. And we're traveling around the sun. If the sun were to just disappear, just for whatever reason, God snaps his finger like Thanos and the sun just disappears. Well, we won't notice that it disappeared immediately. In fact, it's going to take 8 minutes, 8 minutes for us to find out that the sun has disappeared. The light will keep coming to us because by the time the sun disappeared, the last bit of light that was sent from the sun is just leaving, and it takes 8 minutes for light to travel from the sun to the Earth. And so we can see that when we start talking about astronomical things, things out in space, these distances are so big that the fact that light takes time to travel becomes important. And so that what that means is when you look out at planets or stars or galaxies out in space, what you're seeing is not the way things look now, but rather how they looked when the light left that thing. And so there are stars that you're looking at out at night, which have already blown up. They've already exploded. We just don't see it yet. And in fact, it might be 100, 1,000, 10,000 years before we see the explosion that's already happened. And that's just because it takes that long for the light to get to us. Now, what makes this very, very weird, and I can't get into it in this class, what makes this weird is the fact that this number, this speed of light, is so fundamental to the universe. It is so important that literally nothing moves faster than that. And not only that, but the only things that can even get to that speed are things that have no mass. So for instance, light does not have a mass. It has energy, but it's not massive. There's no mass to it. So you can't take the weight of light, for instance. And so since it doesn't have a mass, it travels at the speed of light. And there are other things, for instance, gravity. Gravity, when you get into fancy physics, we think of gravity not just as waves or as a kind of a bending of space and time and things like this, but we think of it as particles as well. And it turns out that gravity, the particle of gravity, which gives rise to the force, also has no mass. And so gravity moves at the speed of light. And so what that also means in terms of this example with the sun is if the sun disappears, our Earth will continue to orbit where the sun was for 8 more minutes because the gravity has not had time yet to get to us to tell us, hey, the sun's not here anymore, so stop orbiting. So if the sun disappears, the Earth doesn't know it gravitationally. It still feels the gravity of the sun, even though it's not there anymore, because the little wave of gravity hasn't gotten to us yet to tell us that we have to stop. So there are other things that can travel at the speed of light, but it is only those things which have no mass. So since we have mass, we can never travel at the speed of light. And there's nothing we can build that will ever travel at the speed of light. Even things that are extremely, extremely light, like a proton, we could get it close to the speed of light, 99.9%, but we can never get to the actual speed of light. What makes it more weird, though, what makes it very weird, is basically what Einstein figured out just by thinking. What he figured out was not only does light travel at the speed of light, of course, but there's something very weird about it, because every time we go to measure what the speed is, as long as we do the experiment correctly, we always get the same number. Now you'd say, well, that's not so weird. Why would you expect, if you're doing the experiment, you're trying to calculate the speed of light, of course you're going to get the same number. If you're not getting the same number, then you're doing something wrong. But here's the thing. Take this as an example. Let's say what you have is a person throwing a baseball. Here's a baseball. They throw the baseball with a velocity of 10 meters per second. Okay. And so here you are over here, and you've got a little camera, or you're doing something to measure the speed of the ball. Well, if you measure the speed of the ball in this particular instance, you get the speed is equal to 10. Perfect. So you measured the velocity of the baseball to be 10. Now, let's say you now have kind of a car or a train or something, and that car is moving towards you with a velocity of 50 meters per second. And on top of the car is the person holding the baseball. Well, if they don't throw the baseball, if they're just holding it, and you're over here measuring the speed of that baseball, well, the baseball's coming towards you with a speed of 50. So you'd measure it to be 50. Perfectly fine, because it's coming towards you because it's on the car. But then, same exact scenario, this car is moving towards you with a speed of 50. Now the person holding the baseball throws the baseball with a speed of 10. What is your little device going to say? Well, it's going to say before he threw it, it was 50. So it's already moving 50 from the beginning. He now throws it with an extra velocity of 10 more. So what you would measure is the velocity of the baseball is now 60. And of course, if you're on the other side over here, measuring the speed, you'd get a different number, because now the number is not moving towards you, it's moving away from you. Okay, so what we expect to see in experiments where we're measuring the velocity of an object is we expect that depending on how we observe it, is the thing moving towards us? Is it moving away from? Are we moving towards the object when it starts to move? All these things should change what we see the speed to be. So what we would expect is if we're measuring the speed of light, let's say we're measuring the speed of light from the sun. So here's the sun, and here's Earth over here. So as Earth is moving, it's moving this way. So it's getting closer towards the sun. It's moving towards the sun. So the light, as it travels, is traveling at c, the speed of light. But then our Earth is kind of moving in the same direction towards it. We're not in the same direction, the opposite direction. So towards it with, let's say, 1,000 miles per hour. Okay. We would expect to see the speed of this light coming from the sun to be the speed of light plus how fast we're moving. Because it's not just light moving towards us and we're not moving. Since we're moving towards the light as well, we have to add in that speed. And of course, the same is true when we're over here. As we start to go this way, we're now moving away from the sun, away from the light. So when what I would expect to find the speed of this light, it should be something less. Because yeah, it's coming towards me with the speed of c, but since I'm moving away, when we add our velocities together, it should be something a little less. I would expect it to feel slower. Just like if the person on the car there throwing the baseball, if the car's moving away from me, then it should be the 10 of the baseball minus 50 because it's moving away. But so that's what I would expect. That's what physics says. Physics says that's exactly what should happen. So every time we measure the speed of light coming from the sun, the value we get should depend on where we are. Are we moving towards the light or away from the light, basically? As we move towards, we should see the light getting faster. And as we move away, it should feel slower. But we don't see this. What we actually find is that the speed of light is exactly the same number, no matter how we're moving. That's weird.
Wait,
There's nothing else. Yeah, what's up?
wait. So, so when you were saying like it's moving towards the sun, would it be like a positive 3 times 10 to the eighth, and then when it's moving away, would it be a negative 3 times 10 to the eighth, or is it 3 times 10 to the eighth all the time?
Yeah. So what we would say, the positive or the negative doesn't really matter to us. In other words, we don't care if we're talking about the light moving to the right or to the left. That would be the positive or the negative. What's more important in this discussion is the speed of light is 3 times 10 to the eighth, period. Whether, in other words, if this were a baseball, it would be 3 times 10 to the eighth plus however fast I'm moving, if I'm moving towards the baseball. Or if I'm moving away from the baseball, it should be 3 times 10 to the eighth minus some amount, minus 1,000 or however fast I'm moving. Because if the baseball is coming at me with a certain speed and then I run towards it, well, to me, it feels like the baseball is going to hit me harder than if I was not running towards it. And of course, if I'm running away from it, it won't hit me as hard because to me, it feels slower. But for light, that doesn't happen. If I'm moving towards the light, it's 3 times 10 to the eighth. If I'm moving away from the light, it's still 3 times 10 to the eighth. It's not 3 times 10 to the eighth plus 1,000 or 3 times 10 to the eighth minus 1,000. Okay. But, if it's moving to the right or to the left, obviously that is true. We could see if the light is moving towards the left or towards the right. But what we don't see is the number itself change, no matter how we try to measure it. And in fact, we could take the exact example. Forget about the sun. Take a person on a train. The train's moving at 1,000 meters per second towards you, and someone has a flashlight. Well, let's say the train's not moving yet. They turn on the flashlight. You measure the speed of light. It's 3 times 10 to the eighth. Now someone's on the train with a flashlight. The train's moving towards you at 1,000 meters per second. And then someone turns on the flashlight. Well, a physicist under classical mechanics would say, okay, they would see the light coming at them at the speed of light plus 1,000. Because without the light turned on, the lights are, or the flashlight itself is already moving at 1,000. And then from that 1,000, it then sends light out at 3 times 10 to the 8th. So you would think it'd be faster. Or the same going the other way. Someone on a train moving away from you, and then they turn on the flashlight. Well, the flashlight itself, the source, is already moving away at 1,000. And then it sends something out with a speed, so you would think you should subtract those two numbers. But what we see in actual real life when we do these experiments is that doesn't happen. It's always 3 times 10 to the 8th. No matter how we move, no matter how the light source moves, we're both moving together. And it's the only thing in the universe we've ever seen have this type of characteristic. Nothing else works like this. Every other thing, if we were to measure its speed, would depend on how the object moves. If the object's already moving with a certain speed and then you throw it, well, it's going to move faster than if it weren't already moving. But light doesn't do this. Now, that shouldn't be something that's comfortable. That shouldn't be something, oh yeah, of course. What's weird about that? It is weird. It's extremely weird. And in fact, when Einstein first figured this out, just thought it up, people didn't really believe it. There's no way this is true. And the reason it can't be true under our normal way of thinking is the only way for this to actually work, for someone to measure the speed of light to be the same number, no matter how they're moving, whether they're moving towards the light or the light is moving towards them or away from them or nothing's moving. The only way to get the same number every time is to have time and space change because of light's speed or because of the speed of an object. So in other words, you with your stopwatch, because, basically, how are you going to measure the speed of light? Well, you have a ruler down on the ground that shows you a distance, and you have a stopwatch. And so you see how far did the thing go in a certain amount of time. Basically, at the fundamental level, that's what it is. Whether you have a machine to do it or not, that's what's going on. It measures a distance, and it measures a time, and then it does velocity as distance over time. So the only way for light to always be at the same speed, no matter how things are moving, is for time itself to slow down when you start to move, or distances shrink or get bigger. This is very weird, because then what this starts to imply is that if you're a person, let's say you get on a rocket ship, if you start to move fast, time slows down for you. And it's not just a fake effect that we just see the time change. Now, maybe our digital watch shows the numbers slower, but it's not reality. It's just how things are measured is changed. No, actual living objects live longer because of this effect. And in fact, in particle physics, we study kind of very fancy particles. Normal particles in the universe are protons, neutrons, and electrons. But when we start doing fancy experiments, we can make other particles. But these other particles, because they're not stable, they don't like to last in this universe, they decay fairly quickly. And so there are certain particles which we know how long it takes for them to die. You create let's say a muon. That muon will decay into other particles after 10 to the minus 15 seconds or something. Very, very short period of time. Well, what people have seen is gamma rays coming from space have a lot of energy. They collide with the particles of the atmosphere out, in the atmosphere up in the clouds. And they collide so hard, there's so much energy, they create these fancy particles. And we know where they're created. We know how high up in the atmosphere they're created. And we know how fast they move. Once this collision happens, it's like an explosion and it pushes the particles down towards Earth. Well, we know based on how long they should live that there's no way the particle can make it all the way to the ground. By the time the particle would hit the ground, it would have already decayed into the other stuff. So we shouldn't detect any. But we do, we detect them all the time. And this is one of the effects of this phenomenon, that even these particles, which we know cannot last 10 seconds, let's say, they only last 1 second. Every single time in our laboratory, when we create the particle, they last 1 second. But what we see is particles lasting 10 seconds for some reason. But they only last 10 seconds if they're moving very quickly. And so it turns out this time distortion, the fact that these particles move very, very, very fast, near the speed of light, means time for those particles has slowed down. Now, they don't feel it. They think, oh, they last a second. All I did was last a second. But what we see is them lasting 10 seconds, because to us, their time is a lot slower. Their 1 second took us 10 seconds. And so this is a real effect. This is not fake. This is not just some math stuff we got to take care of. If you, as a living human being, were to get on a rocket ship and move very close to the speed of light, you would live your life as normal. You wouldn't see any weird effect. You're not going to walk in slow motion. You're just living. And you say, okay, it's been 1 year. I've had my birthday. Go back to Earth. And on Earth, it's been 15 years. You're like, what the heck? It's only been 1 year. I was only in space for 1 year. I celebrated my birthday. But the people on Earth who were not moving that fast, they would say, no, it's been 15 years. But you, since your time has slowed down, you didn't notice it. That's one of the effects of the fact that light is always moving at the speed of light every time we detect it. The only way for that to happen is for space and time as fundamental entities of the universe to change based on how fast you move.
Okay.
Yeah, question?
So essentially what you're saying is like technically, like for example, with the rocket ship, so pretty much if you are going past this, like near the speed of light out, and you only, let's say, like you say, you stay out there for a year and then you return back to Earth and it's been 15 years later, could you say possibly that can never happen? Can that ever happen in reverse? Like, can that happen in reverse, saying, let's say someone, like, is there ever, wait, time always moves forward. I want to know, so going back in time is never really possible, huh?
Well, in terms of physics, there's nothing in physics that says we can't do it, which is one of the interesting things about physics. Is an actual physicist cannot say that time travel to the past is impossible. There's no piece of physics we can think of, or some mathematical expression that says, because I got a zero here or because I got an infinity, that means this can't happen. It seems to be part of our physical laws that it could be possible. Now, it's not as straightforward as going into the future. This effect is going into the future, for instance. This is time travel, where a person can go 15 years into the future. It takes them 1 year to do it, let's say, but you can go 1,000 years into the future. So if you get on a rocket ship and you go really, really, really close to the speed of light for a year, and then you come back, 1,000 years have passed. So that's time travel. Now, we don't have as easy of a way of thinking about going in the past. How do you move and then you end up in the past? But that doesn't mean that physics can say it can't happen. Physics has no word to say on whether it could. And in fact, one of the things I've learned about physics is unless there's something that says it definitely cannot happen, then it's usually the case that it must happen. It must be possible. Everything can happen or everything will happen that could happen, basically, by physics. How to do it, we don't know, because if we did know, then we would have tried, certainly. And there's a lot of the philosophical arguments against it, say, well, if it were possible, number one, why haven't there already been people coming back in time? Because even if we can't do it for 10,000 years, surely someone at some point in the future would decide, hey, let me go back to the year 2000, or let me go back to 1980 or whatever. Someone would have done it. So you have these philosophical reasons why it must not be possible. But in terms of physics, there's nothing special about time that says you can't go backwards. Forwards is all right, backwards is not all right. The thing about the laws of physics is they're what's called reversible, generally speaking. If you can take a video camera and video something happening forward in time, then the reverse should also be possible as well. Now, how to do it, I don't know. Okay. I'm sure there are big time theorists who thought about it and say, well, it would take a huge amount of energy and there are ways to do it. It's just we don't have the ability yet. But there's nothing that says we can't go back in time.
So like, okay, like for you're saying like forward in time, if that's possible, like, okay, let's say the person that's on the rocket ship saying it's only been a year. So they let's say they turned 36 and they go down. Will they like when they go back to Earth, are they still 36 or do they age as they get back to Earth?
No. They're 36. They would have lived one single year and they get back to Earth and they just keep on living like normal. It's not like all of a sudden their cells say, oh my God, I'm not moving anymore. I need to start getting back to the way I should have been. No, in other words, the thing that makes you age, whatever it is in your cells where they die off and they can't make themselves again, whatever age is, those processes happen under the normal laws of physics. And even though you're technically time traveling because you're moving so fast near the speed of light, your body doesn't realize it. It just does its thing. And when you get back to Earth, it's still doing its thing. It's just now your time is the same as someone else's time. Your time was special when you were moving fast. Now you're moving at the same speed as everybody else. So your time is the same as everybody else again. So yeah, you would not see some weird effect that all of a sudden, as soon as you stop your rocket, things catch up to you. And in fact, this is one of the things they talk about, twins. You have a pair of twins. One twin gets into a rocket, one stays on Earth. The twin in the rocket moves around really fast, comes back, and the twin is now 80, and the person that was on the rocket is only 30. And this is perfectly possible. There's nothing, in terms of a physicist, they say, yeah, of course, that's the way it works. It seems weird. What is it about just moving that makes your time slow down? It's like a weird, there's no reason these things should be connected to each other. But that's only because the way we think about time and distance and things like this is fundamentally wrong. And we have to have a different way of thinking if we want to be comfortable with these kind of ideas. But this is the way things actually are. If you move faster, you'll live longer, basically. Now, you won't feel the effect. You'll still feel like you only lived 100 years or whatever. But to the outside world, they would say you live for 200 or 300 years. And that's just because time is flexible. Time changes based on your motion. And this subject is called special relativity. Now, I'm not going to get into special relativity, the math of it or anything, but this is one of the interesting things about light that makes light a very, very special thing in this universe. Now, unfortunately, the class is over. I know I've brought you all over time. I'm sorry about that. We will continue discussing this stuff next time and, of course, get into some of the actual physical characteristics we need to know, like things like frequency and wavelength, how they're related to the speed of light and things like that. But anyway, that's really all I have for you today. Monday, we will continue talking about this. So I hope you enjoy your weekend, and I'll see you next time.
Hi, Dr. Ross Mammoth.
Yes.
I submit the Bernoulli and Archimedes homework, but I still have to submit the test. And I didn't know if I was supposed to submit the test with the homework assignments because I thought you would have gotten confused on what is what.
Okay.
But I was wondering if you could reopen the test that was Monday so I can submit the test.
Yeah. In fact, send me an email just to remind me about the test so I don't forget. That's exactly what I'll do. I'll extend a deadline for you. That way you'll have time to submit it and just submit it onto Canvas. Yeah.
Yes, sir.
Perfect.
I've been trying to go back and look at the notes and stuff to catch up and everything. So I appreciate that so much.
All right. No problem.
Yes, sir. Take care. Have a great weekend.
You too.